is it true that for all sets A, B, and C, if A minus B is going to be a subset of C, then A minus C is going to be a subset of B? Well, let's draw a diagram to see if that's going to be true. Okay, so what does it mean for A minus B to be a subset of C? Well, it means that we want to look at parts of A that are not also in B. So it means that we don't want to be looking at this entire blue part, right? This leaves us with this moon-type shape of A. However, this moon-type shape of A has to be a subset of C. Now, what part of this moon-type shape is going to be a subset of C? Well, it means that all of this moon part has to be in C. So which part of this is going to be in C? Well, it's going to be specifically this part right there. Yeah, actually, let me do that in a different color. I'll do that in green. So let me just quickly fix that. There we go. A minus B means we're interested in this section for it to be all in C, which means that this part of A does not exist under our circumstances. So this is the condition that we have, that this green part is A, because that is A minus B, right? This part of A does not include parts in B, but it's also entirely in C. It's entirely a subset of C. So now, if we look at A minus C, or if we take A and subtract every part that's also in C, are we just going to be left with the set B? And the answer is, well, most likely yes, because look, if we need to remove C, that means we're removing all of this, right? But we also have to remove this green part because this green part is also in C, and we want to get rid of anything that's going to be in C. So what happens when we get rid of everything that I've highlighted in red? Well, we're going to be left with just the set B. So it does in fact look like the statement is going to be true. So let's go ahead and now prove this. So to start our proof, this is a for all statement, which means we have to start this with a let. We start all of our for all statements with a let. We say let A, B, and C be sets. There we go. We've supposed this so now the reader knows what we mean when we say A, B, and C. We then have to say, maybe we continue the sentence actually, such that we want to say that this condition is going to be true, such that A minus B is a subset of C. Fantastic. Because what we're going to try and prove is that when this condition is true, naturally, this would also be true. So how do we get from here to here? Well, let's draw out a little map of our proof. Okay, so how are we going to get from here to here? It might make more sense to maybe work backwards. What does it mean for this to be true? Well, it means that if you have some element x be an element of this set, then x is also going to be an element of B. Okay, what does it mean for x to be an element of A minus C? Well, it means that x is an element of A and x is not an element of C. Okay. Okay, so to prove that when this is true, that is true, it might be easier to maybe work backwards. Let's suppose that we have some element in the set A minus C. Okay, what does it mean for something to be an element of this set here? Well, this means that x must be an element of A and x cannot be an element of C. We can't say x is an element of B, we need to prove it. So let's prove maybe x must be an element of B. So we can then say, maybe this will be an easier proof by contradiction. Let's give that a shot. We can say, if x is not in B, then, here, let me make that look a little neater actually. I'll do this in a different color now. So we can then say, if x is not in B, so we're going to say contradiction proof by contradiction. So if we can show x is in here, then x is in here, then we've proven our statement. So if we can then say if x is in here but it's not in B, then of course x would be an element of A minus B, right? Since it's not in B. Which then means x is an element of A and it's not an element of C. But notice that we've just said x. Oh, no. I'm thinking way too far ahead. So this means x is not an element of x is an element of A and it's not an element of B. And since we assumed this to be true, then x would be an element of C. But notice, if we're saying x is an element of C, but it's also not an element of C, this is going to be our contradiction that we were looking for originally. So it must be then that this all started by assuming this to be true. So if this is true, it leads to a contradiction of x being in C and x not being in C, then it must mean that the opposite is true. X must be an element of B. Yeah, okay. Let's try to put this into words. So hopefully this makes sense. Maybe stare at it for a while and it'll make sense. But I'm going to go ahead and try and put this into words. So we're going to start by supposing... well, no, do we need to suppose? Yeah, let's suppose x is an element of A minus C. Then we can break down what that means. Then x is an element of A and x is not an element of C. Fantastic. Next, let x not be an element of B, so x would be an element of A minus B, meaning x is an element, no, I don't even need to say that. Okay, so far this should make sense. We're gonna just let x be an element of this, then x would be this and this. Next, we're going to let x not be in B, so x must be in this. And then we can say, and given A minus B is a subset of C, then any element of A minus B must also be an element of C, making x an element of C. Fantastic. And then we have our contradiction. However, x cannot, or how actually, however, what's a better way of saying this? I'm struggling with the English part. However, if x is an element of C and x is an element of C, then we have a contradiction when, or from contradiction from x being not being an element of B, meaning x must be an element of B. So, have I said so too many times? I'll just say given now. I've said given once. Or I'll just say thus. Thus, if x is an element of A minus C and x is an element of B, then A minus C is a subset of B. I think that makes sense. Need a moment to think about that. Yeah, because we have our contradiction right here from this assumption. That's what I'm claiming. I'm claiming from this assumption you get this contradiction, which means that the opposite must be true. X must be in B. So if x is in here and it's in here, that means this is a subset of that. And the contradiction obviously comes from our assumption that this is true. So that means that for this to be true and not contradict something like that, this must be true, and for that to be true must be that's true. Okay, I think this makes sense. So there we go. We've proven that this statement is in fact going to be true.